Hi everybody, in this lesson we have three objectives. We're going to be looking at three different discontinuous graphs, F, G, and H. The first objective is we're going to discuss the type of discontinuity that is occurring at specific x values on those discontinuous graphs. After we discuss the type of discontinuities, our second objective is to find some functional values on each of those three graphs. And the third objective is to find some limits on each of those three discontinuous graphs. So our first objective is to look at each individual graph and discuss the types of discontinuity that are occurring. All right, in a previous lesson, we talked about holes or removable discontinuities and jump and infinite discontinuities. I'm going to make a slight change, and moving forward, I'm going to use this slight change. And what I'm referring to is the removable discontinuity that is also known as a hole. It also has a third different name, and we call that a point discontinuity. So instead of calling something a hole or a removable discontinuity, I'm going to call it a point discontinuity from this point forward. All right, so let's look at graph F. So when we look at the discontinuous graph given here, we jump on the graph, we working our way around, and at the x value of some number c, I can see I have an open circle. All right, so that requires further investigation. So I can see at this open circle that the graph of this function doesn't come off the other side of the open circle. I have to actually jump up here to a y value of 2 so that I can continue the graph. So for graph F, we have a jump discontinuity. So we'll just record it down here. All right, and again, you could have an open circle here as well and have two open circles. This would still be a jump discontinuity. But you couldn't have two closed circles because then it wouldn't be a function. All right, graph G. All right, you jump on the graph, you continue around, you have an open circle that requires investigation at an open circle. I can see the graph goes into the open circle and leaves the open circle on the other side of it. So this is what we call a point discontinuity. Some students sometimes think that because I do have a defined point here, that this is a jump discontinuity, but it is not. This is still a removable discontinuity or a hole, or what I'm going to call a point discontinuity, because if I were just to transpose this and translate this point and move it down and fill in this open circle, then the graph would be made continuous. So this is a point discontinuity, not a jump discontinuity. Remember, a jump discontinuity means that the graph ends at one y value and starts again at a different y value. But over here, you can see that this graph right here ends at this y value of -1 and begins again at the same y value of -1 on the other side of that open circle, or that point discontinuity. All right, and look at graph H. I think this is going to be uncomfortable for you because you see this point down here, but yet you have a vertical asymptote. And I just wanted to throw in something interesting and juicy as well. All right, what type of discontinuity? It's either point, jump, or infinite. Well, this point right here has no bearing on the type of discontinuity. So this graph continues upward, infinitely getting larger. It happens to be infinitely large on the other side of the vertical asymptote. So we disregard that point. It doesn't mean anything as far as the discontinuity that's occurring. This is what we call an infinite discontinuity. So when you see a vertical asymptote, there's other different kinds of interesting graphs. I'm not going to say that every time you see a vertical asymptote, that's going to be an infinite discontinuity. And we might study those later, but typically we don't in this course study those really strange graphs. So for what we're doing, this is going to be good enough. All right, let's go to our second objective. That's done. Our second objective says find the following function values if they exist. If they do not exist, we're going to write does not exist, and we're going to state why. All right, so let's look at the notation. We have to be notationally fluent. So if I'm given the graph of f of x and I'm given the question, what's f of c? Well, it's just saying, let's go to the f graph, which we have here. When my input value is c, whatever number this may be, okay, what is the y value associated with that x value of c? So I'm going to slide all the way over to where x is c. Whatever number that is, c just represents a x value. And I'm going to look up or down, and I'm going to see if I can connect with the graph. Well, as I move upward at this open circle here, there's not a point there, so I have to continue upward. And actually the functional value when x is c is 2. The y value, or also known as the functional value, is 2. So the f function exists when x is c, and it's 2. Okay, let's look at the g graph. Let's find g of c. So locate c. This is an x value. So look along the x-axis. Here's x equals c. Look up, look down. Oh, the functional value is 2. It's just saying, locate the point on the graph having x coordinate of c. Okay, what about h of c? Okay, so there's a vertical asymptote here, but who cares? When x is c, look up or down. Well, we happen to put this random point here. This is probably a piecewise function, as all of these are. Okay, so h of c is also 2. How about h of c is, negative 2. All right, before we move on to our third objective, I want to kind of linger on this second objective here and talk about what-if situations. All right, so let's take a look at f of c. Okay, what if, now I'm done here. I have the functional values, but it's always good to kind of look at what if. And I like if you guys ask what if questions, because sometimes when you change something slightly, it brings up a lot of interesting math. So don't ever be afraid to ask what if questions. What if it looked like this? Well, I mean, it's great because it requires our investigation, and a lot of conversations can take place within, that question. All right, so let's look at this situation. What if on the F graph, what if this was not a closed circle but an open circle? What if f of x at x equals c had 2 open circles? Well, then I would have to say, if the question was find f of c in that situation, I would have to say that f of c does not exist. Okay, and it says up here, okay, find the following function values if they exist. If they do not exist, if you put a does not exist answer down, we have to state why. And I want to kind of begin to lay the groundwork on the correct explanation. So you might already have something formed in your brain, and that's good if you do. But if this had been an open circle here, and we had 2 open circles, and we had no y value to grab a hold of, we would say because, and it's okay to abbreviate, because there's no y value for x equals c. That's the explanation why we do not have a functional value. There's just no y for that input value of x equals c. So look at graph G. Okay, so remember, this is just a what if you don't want to write it down, because if you look back at these notes later, you're going to go, what does that mean? Okay, so this was if we had 2 open circles. Look at the G graph. Okay, well, what if that point wasn't there? And all we had was this graph right here with this point discontinuity. What if that point wasn't there? Then G of C would also be does not exist. And why? Because there'd be no y value when x is, or for x equals c. No y value for x equals c, if there was no point. And likewise with the H graph, what if that point wasn't there and you were asked to find H of C and that point wasn't there? This does not exist because there's no y for x equals c. So that's going to be the justification that we would use in this course if a functional value does not exist. It just simply means there's no y for that x value. All right, so we've looked at the first objective of discussing the types of discontinuity. Remember, the word point means whole or removable, but I'm going to use the word point discontinuity moving forward. So a point discontinuity can still have a point lined up with it vertically. It's a weird case. All right, functional values. Okay, just finding y's that belong with input values, and how do we correctly respond if we don't have a y value? And these would be the explanations. Okay, and you can record that or not, but I just wanted to kind of discuss that while we had an opportunity. All right, the third and final objective is to look at those graphs and then discuss limits. All right, it says find the following limits if they exist. If the limit does not exist, write does not exist and state why. All right, so we're going to look at this in column format. So we're going to look at these 3 questions first because they all deal with the F graph. as suggested by the notation. Then we're going to look at answering these three questions next because they all pertain to the G graph. And then lastly, we'll look at these three questions because they all pertain to the H graph. Okay, so this is, the way we read this is, the limit as x approaches c from the left, that's what the little minus sign means, of the f of x function is equal to. So a limit question may or may not be the same thing as a functional value answer. It may or may, the answer to a limit question may or may not be the same as the answer to a functional value question. Remember, functional values means you are at specific x values looking up or down on the graph. The whole idea of a limit question is you're approaching a specific x value of a point on the graph. And what's the behavior of the graph? All right, so as x approaches c from the left, okay, so I'm going to come up here to my graph. I'm going to real quickly put myself on x equals c, but I'm going to move to the left of x equals c. So right over here, real close. Don't move too far away from x equals c, because the idea of a limit is the x values of points on the graph are getting closer to that c value. So I'm at x equals c just for a moment. I move to the left, I jump up on the graph, because here's where it's at. I look up and there it is. Now I'm going to start moving on the graph to where the points on my graph, the x-coordinates, are getting closer to c. So what's the left-hand limit is what we call this. What are the y values going into? We'll look across here horizontally, and it looks like the y values are going into 1 on this part of the graph. So my left limit has a value of 1. So let's look at the second question. What's the limit as x approaches c from the right? Okay, so same idea. This is a limit question, right? So go to c, gives us a starting place for our x value, but move to the right of it. Okay, look up, look down, wherever, find the graph. There it is. So right here, this x-coordinate is close to this number c, but we want to get closer. We're approaching. That's what the arrow means. Okay, on the limit question, those x values have to get closer and closer to c. And as you move up this way on the graph, these x-coordinates are getting closer to an x value of c. Well, what's the intended height here? Well, as I get closer and closer to x equals c without ever being at x equals c, this graph suggests if I move upward, if I move over horizontally, that my intended height is 2. So my right-hand limit is now 2. All right, so now let's look at the notation in this bottom question. And I have therefore a stack of 3 dots. So we have to, in order to answer this question down here, we have to investigate the behavior as x approaches c from the left and c from the right. So as x approaches c, which means we're looking at behavior from left and right, we evaluate and look at these two, inspect these two numbers. These two y values are different. So we would say the limit does not exist. Okay. And why? Because it says if a limit does not exist, we have to state why. Well, in a limit question, the justification or the stating why is this: because the left limit doesn't equal the right limit. 1 does not equal 2. We don't want to put 1 does not equal 2 because that's not real revealing. You could use the words the left limit does not equal the right limit, but it's better to use the notation because the limit as x approaches c from the left of f of x, this needs to be here to discuss the function I'm working on, does not equal the right-hand limit. And this is the notation that represents the right-hand limit. It's all new. If it's uncomfortable, that's okay. We'll spend some more time on this. All right, let's look at these middle questions here. All right, so what's the limit as x approaches c from the left on the g function? So let's go up to the g function. This tells me what function I'm working on. So I want to approach c from the left. So here's c, get to the left of it, look down because that's where the graph is. Put yourself on a point that's close to x being equal to c. Now, the arrow means I want to approach c from the left. So that means I have to move. Unlike a function value where I'm standing steady, looking up or down, what we did in the second part here. Okay, I want to approach x values of c. Well, what's the intended height here? Well, it looks like as I get closer and closer to c, it looks like when I look over here horizontally, it looks like my left limit, my y values are going into -1. That's the intended height. So what's the right limit? The limit as x approaches c from the right of g of x. Here's c, move to the right here, jump on the graph. Now move on the graph so that your x values would be getting closer and closer to c. So what's this intended height? Well, it's going into that same open circle, so its intended height is still -1 as well. So the left limit equals the right limit. So does the limit exist? Yes, it does, because these two numbers are the same, and the limit is -1. All right, so let's come over here and look at the last set of questions. What's the limit as x approaches c from the left on the h function? Here's c, I'm to the left. That means I've got to jump on the graph. Which way should I travel, up or down, so that my x coordinates of the points are getting closer to this xc? Well, I got to move up. Well, what are the y values going to? Are they leveling off? Is there an intended height? No, they're getting infinitely large. So we would say the left limit is approaching infinity. Now, for this situation, when you have an infinity answer, whether it's positive or negative, okay, infinity is not a specific value like these individual one-sided limits are over here. So we want to go, comma, this limit does not exist. The reason we say that is because an informal definition of a limit is that the limit is leveling off to a specific y value. And infinity does not give us a specific y value. It just gets larger and larger. So you need to put both. So this describes, when I think about this and what you put here, an infinity symbol, I'm thinking of a vertical asymptote and the graph going upward. But the limit does not exist. It's not leveling off. So this is the official answer, but this is descriptive. It allows me to see what the graph is doing, but they both should be there. All right, what's the right-hand limit? Well, as x approaches c from the right, same thing. I'm approaching infinity, but wait a minute, that's not a number. So that limit's official answer is does not exist. All right, so down here, therefore, stack of 3 dots, the limit as x approaches c, I have to have already considered left and right-hand behavior, those one-sided limits. So the limit of the function is infinity, and I would put a d and e. Okay, remember, it says, if the limit does not exist, state why. Okay, so why does this limit not exist? Is it the same thing as why this limit did not exist? No, it's a different situation. So our explanation should look a little different. So we're going to put because the limit as x approaches c, and I'm not going to worry about the plus and the minus here from the left and the right, of h of x equals infinity. That would tell somebody that knows about limits that a limit cannot approach infinity and exist. So this is the justification, and the official answer is a does not exist situation. So look at the difference between these two right here. Here I actually looked at the left limit does not equal the right limit, but here I just had to say because the limit goes to infinity, and that justifies to somebody that that limit does not exist. Okay? All right, now we're in a what if situation. Okay, what if? So we're done, finished, but what if? Okay, look at the H graph. What if actually this looked like a reciprocal graph where you didn't have this togetherness here? What if, I'm just going to say, what if this branch wasn't here on the graph, but the branch was down here instead? So what if? What would change as far as any of the 3 objectives we looked at? Okay, would we still have an infinite discontinuity if this branch was down here? Yes, because we still have a vertical asymptote, and we have to lift our pencil at that vertical asymptote to draw this graph, even though we go back later and put a point on that vertical asymptote. This would still be an infinite discontinuity if the graph looked like this, if this branch wasn't here, but it was here. Okay, does our functional value change just because I moved that branch from here to here and reflected it? No. Okay, I still have a y value of -2 when x is exactly c. Okay, well, what's going to change down here with the limit questions? Does the limit from the left still equal positive infinity? Indeed it does. Okay, what the adjustment we would make here for the right-handed limit is that we would say as x approaches c from the right, so that means we're on the graph and we'd have to go down here to get to x values that are closer to c. Okay, this would have to be, I'm just gonna make an adjustment, go back and erase it. This would have to be a negative infinity. Would I still put d and e? Absolutely I would. Okay, because that's not a number. And that's the informal definition of a limit, is that you approach a specific number. Okay, and don't worry about all that. In a later video, we're going to have specific notes that kind of capture all of this together. We're just kind of going through this informally and using our intuition. Okay, so do I need to make another adjustment here? Well, then therefore the limit as x approaches c of h of x would equal, notice that you have a positive and a negative. The only adjustment I would make is I would make this positive and negative to suggest that one of the one-sided limits goes to positive infinity and the other one-sided limit goes to negative infinity. And then I would also have to come down here in my justification and say the limit doesn't exist because I approach at least one of the infinities. And in this case, if I change that branch, I would be approaching a positive infinity and a negative infinity. And that would be my justification. Okay, so I'm going to go back and erase these because I want to make sure that, you know, you're not confused later. So we're going to actually make, oh, pardon me, this is going to be just regular infinity, and I believe this was just regular infinity. Okay. Yep. And I'm going to come up here and I'm going to erase this and make it the way it was originally. Okay, and one final comment that I'm going to make about these graphs. Okay, so back up here. If you have a discontinuity that is a jump discontinuity, will the limit exist at the x value where that jump is occurring? No. So, and why? So I want to put the justifications that we found down here up here. So the limit will not exist at a jump discontinuity because let me put this. Let me do this. Jump means a limit does not exist. And then down here I'll put because the left limit does not equal the right limit. And it's important to put f of x here. You can't ever leave this blank because then I don't know what function we're talking about. Okay, what about at a point discontinuity? Will a limit exist as you're approaching the x coordinate of that point discontinuity? Well, look down here if you can't remember. Did the limit exist on that point discontinuity? It does. Because the graph goes into that open circle and leaves that open circle. The only thing that's not there is just that y value. So a limit does exist here at the x coordinate of the point of discontinuity. So the limit would exist on a point discontinuity. Okay, and finally, will limits exist at x coordinates of infinite discontinuities? Nope. Because the limit as x approaches c of our h of x graph equals infinity. Or it could have been negative infinity or both of them as well. Okay, so limits exist on point discontinuities, but limits will not exist on the jump or the infinite discontinuities. So, all right, well, that was a lot, and don't worry, we're going to be spending at least another week on limits. So if it's not coming to you right now, it will come to you soon.